Okay, thank you. So we can move directly to the next slide. The present work deals with the experimental investigation of the effects produced by varying the loading direction with respect to the spring one on both mechanical and fracture properties of the shoe earth 772. In particular, my presentation consists in the following section: a brief introduction, the description of the experimental campaign, the discussion of the obtained results, and finally, the conclusions. The material here examined is a shoe earth that is an innovative and eco-friendly one that has gained attention and interest as a sustainable construction material. It is composed by a mixture of excavated soil, aggregates, and water, where the soil may be either unstabilized or stabilized by a chemical binder. More precisely, the dry mixture that is blown by a high-velocity airstream into a spring hose was mixed with water under high pressure in correspondence of the spring nozzle. The impact onto the surface compacts the material. The application of shoe earth are those typical of shotcrete and mainly consist in new structures, repairs and rehabilitations, and slope and surface protection. The novelty of the present research work is to experimentally investigate the possibility that the shoe earth presents an anisotropic behavior both in terms of mechanical and fracture properties due to its manufacturing process. In the following, specific mixture of the shoe earth named shoe earth 772 is examined, and it consists of, by volume, 7 parts of soil, 7 parts of aggregates, 2 parts of cement, and about 3% of water. The soil is an excavated soil that, according to the ASTM standard, is classified as a lean clay with sand. The aggregate is a commercial mixed one for concrete, whereas the cement used for stabilization of soil is a Portland cement CEM 142.5N. The shoe earth is consolidated on the receiving surface by the high impact velocity. In the present study, the receiving surface of about 100 centimeters far from the nozzleman is the formwork panel with sizes 800 by 800 by 100 cubic millimeters. 4 samples are cured for 28 days under ambient conditions, and note that all the tested specimens are extracted from those samples as detailed in the following. So, as mentioned in the introduction, the topic of this work is to investigate the anisotropy of this material from both a mechanical and a fracture point of view. Regarding the mechanical properties, compressive, tensile, and flexural strengths are determined, together with the elastic modulus, by varying the loading direction with respect to the spring one, as shown in the scheme on the right hand side. In particular, 2 loading directions are examined. The fracture toughness is instead investigated for what concerns the fracture properties, and that is done by performing 3-point bending fracture test according to the modified 2-parameter model that was developed by the present authors, and that is done by considering the two mentioned loading direction. So, regarding the compression tests, they are carried out according to the European recommendation at the testing laboratory of the University of Parma in Italy, under load control and by using an electromechanical press. 4 cubic specimens of nominal sizes of 100 millimeter by side are tested for each loading direction. For what concerns the tensile tests, they are carried out again according to the European recommendation under load control, and 5 prismatic specimens with nominal sizes 100 by 100 by 330 cubic millimeters are tested again for each loading direction. For what concerns the flexural test, 5 prismatic specimens whose nominal sizes are here reported are tested under 3-point bending loading condition by considering the two mentioned loading direction. The tests carried out according to the European recommendation are performed by using a universal testing machine instrument under load control and with a loading span equal to 300 millimeters. The elastic modulus tests are carried out according to the UNI EN 12390 standard part 13 by following the method EA. In order to determine both the initial second elastic modulus and the stabilized one. 5 prismatic specimens with these nominal sizes are tested for each loading direction, and 2 LVDTs are used for the axial deformation measurement. The load is applied by following the recommendation of the European standard, and the tests are performed under load control. Finally, the fracture tests are carried out on 5 notched prismatic specimens. The nominal sizes are here reported. So 5 for each loading direction. The tests are carried out under 3-point bending, under crack opening placement control, and with a loading span equal to 400 millimeters. Each specimen during the test is monotonically loaded up to the peak load. Then it is fully unloaded when the force is equal to about 95% of the peak load on the post-peak stage. Finally, the specimens are reloaded up to failure. The values of peak load, initial elastic compliance, and unloading elastic compliance obtained from these tests are used to compute the fracture toughness according to the modified two-parameter model. Here and in the following, the results obtained from the just described experimental tests are presented and discussed. And first of all, in order to quantify the anisotropy of the material, an anisotropy ratio is defined as the ratio between a given mechanical properties measured along the direction perpendicular to the spline 1 and the same mechanical properties measured along the direction parallel to the spline 1. Here, on the right-hand side, the results obtained from the compression tests are plotted, and we can observe that the mean value of the compressive strength obtained from the specimens loaded parallel to the spline direction is equal to 7.90 megapascal, whereas the mean value is equal to 15.53 megapascal for the specimens loaded perpendicularly. In this case, a significant increment is observed of about 97%, and an anisotropy ratio equal to 1.97 is computed. The undirected tensile strengths are instead plotted in these pictures. We can observe that the mean value for the specimen loaded parallel to the spray direction is equal to 1.43, whereas a mean value equal to 1.50 is obtained for the specimen loaded perpendicularly. In this case, the relative difference is lower than 5%, and the anisotropy ratio is equal to 1.05. The flexural strengths are reported in the figure on the right-hand side, showing again that the mean value is equal to 3.41 megapascal for the specimen loaded parallel to the spray direction, whereas a value of 3.30 megapascal is obtained from the specimen loaded perpendicularly. In this case, the relative difference is lower than 4%, with an anisotropy ratio equal to 0.97. The results obtained from the elastic modulus test are plotted in this graph in terms of the stabilized secant elastic modulus. For the specimen loaded parallel to the spray direction, the mean value is equal to 18.2 gigapascal, whereas a value of 32.1 gigapascal is obtained for the specimen loaded perpendicularly. Also in this case, the relative difference is significant of about 77%, with an anisotropy ratio equal to 1.76. Finally, the fracture toughness values are plotted in the figure on the left-hand side, showing that the mean value of fracture toughness obtained from the specimen loaded parallel to the spray direction is equal to 0.534, whereas a value of 0.512 is obtained for the specimen loaded perpendicularly. In the case, the relative difference is of about 3 and 4%, with an anisotropy ratio equal to 0.96. On the right-hand side, instead, two pictures representative of the crack paths observed in two specimens loaded in both directions are reported, showing that in both cases the crack deflects during its propagation due to the material internal heterogeneities. And now let us move to the conclusions. The present work has been dedicated to experimentally investigate the possibility that the shooterd is anisotropic due to its manufacturing process, both in terms of mechanical and fractional properties. No significant anisotropy is observed under tensile failure, and in this case, the anisotropy ratio is equal to about unity for tensile, flexural strengths, and fracture toughness. On the contrary, a significant material anisotropy is observed when a compression failure is taken into account. As a matter of fact, such a ratio is equal to about 1.97 for compressive strength and 1.76 for the elastic modulus. Thank you for the kind attention.